Welcome to Selection with Sathi. Today we cover advanced BST operations that go beyond basic insert, search, and delete. We will learn how to validate a BST correctly, find the Kth smallest element, compute floor and Ceil, convert a sorted array to a balanced BST, and find Inorder Predecessor and Successor. These are high-frequency questions in GATE CSE and coding interviews. Let us begin. The most common mistake in validating a BST is checking only that left child is less than node and right child is greater. That is not enough. Every node in the left subtree must be less than the root, not just the immediate child. The correct approach uses a range. Look at line 5. If the node value is outside the allowed range, return false. Line 7. For the left child, the upper bound becomes the current node value. Line 8. For the right child, the lower bound becomes the current node value. This propagates constraints all the way down. Time is O of n. Finding the Kth smallest element in a BST is elegant because Inorder traversal of a BST gives elements in sorted order. So the Kth element in Inorder is the Kth smallest. Look at the code. We use iterative Inorder with a counter. Lines 5 and 6 push the left chain onto the stack. Line 8 pop a node and increment the counter. Line 10, if counter equals k, we have found it. Return immediately. No need to traverse the entire tree. Time is O of h plus k. For frequent Kth smallest queries, use an augmented BST that stores the size of each subtree for O of h lookups. Floor of x is the largest key in the BST that is less than or equal to x. Ceil of x is the smallest key that is greater than or equal to x. Look at line 4. If we find an exact match, return it. Line 6. If the current node is less than x, it could be the floor. Save it as a candidate and go right to find a bigger candidate. Line 9. If the current node is greater than x, go left. For Ceil, the logic is mirrored. Save candidates when node is greater than x, go left to find a smaller candidate. Both run in O of h time, O of 1 space, purely iterative. Given a sorted array, we can build a balanced BST using recursion. Look at line 4, pick the middle element as the root. This ensures roughly equal elements on both sides. Line 6, recursively build the left subtree from the left half of the array. Line 7, recursively build the right subtree from the right half. The resulting tree has height O of log n, which is the minimum possible. Time is O of n since we process each element once. This is a gate favorite. They give you a sorted array and ask the height of the resulting BST. The Inorder predecessor of a node is the node that comes just before it in the sorted Inorder sequence. The successor comes just after. Look at line 4. If the current node is less than the key, it could be the predecessor. Save it and go right. Line 7. If the current node is greater than the key, it could be the successor. Save it and go left. Lines 11 and 13. If we find the key and it has a left child, the predecessor is the rightmost node in the left subtree. If it has a right child, the successor is the leftmost node in the right subtree. Time is O of h.
Let us validate two trees. Tree A, root 5, left 3 with children 1 and 4, right 8 with children 6 and 9. Node 5, bounds are minus infinity to infinity. 5 is within bounds. Node 3, bounds are minus infinity to 5. 3 is within bounds. Node 1, bounds are minus infinity to 3. OK. Node 4, bounds are 3 to 5. 4 is within bounds. Node 8, bounds are 5 to infinity. OK. 6 and 9 also pass. Tree A is valid. Now tree B, root 5, left 3 with children 1 and 6. Node 6, bounds are 3 to 5. But 6 is greater than 5. Fails. Tree B is not a valid BST. Notice, 6 is greater than its parent 3, so a simple parent check would miss this. The range method catches it. BST, root 20, left 10 with children 5 and 15, right 30 with children 25 and 35. We want the third smallest element. Start iterative in order. Push the left chain, 20, 10, 5 onto the stack. Pop 5. Count is 1. Not 3 yet. Right of 5 is none. Pop 10. Count is 2. Not 3. Move right to 15. Push 15, no left child. Pop 15. Count is 3. Equals K. Return 15. We only visited 3 nodes in sorted order, 5, 10, 15. Stopped early without traversing the entire tree. BST with keys 10, 20, 30, 40, 50 arranged as a balanced tree. Let us find floor of 27 and Ceil of 27. For floor, start at root 30. 30 is greater than 27, go left. Result is still none. At node 20, 20 is less than 27. Save result as 20. Go right. Node 20 has no right child. Return result, floor is 20. For Ceil, start at root 30. 30 is greater than 27. Save result as 30. Go left. At node 20, 20 is less than 27. Go right. No right child. Return result, Ceil is 30. Floor of 27 is 20, the largest key not exceeding 27. Ceil of 27 is 30, the smallest key not less than 27. Convert sorted array 1, 2, 3, 4, 5, 6, 7 to a balanced BST. Array has 7 elements. Middle index is 3, value is 4. Root is 4. Left half is 1, 2, 3. Middle is index 1, value 2. Left child of root is 2. Left of 2, array 1, mid is 1. Left of 2 is 1. Right of 2, array 3, mid is 3. Right of 2 is 3. Right half of root is 5, 6, 7. Middle is 6. Right child of root is 6. Left of 6 is 5, right of 6 is 7. Result, root 4, left subtree 2 with children 1 and 3, right subtree 6 with children 5 and 7. Height is 2, which equals floor of log 2 of 7. Perfectly balanced.
Quick exam tips for advanced BST operations. First, validate BST using the range method with min and max bounds. Checking only parent versus child is wrong and will fail edge cases. Second, Kth Smallest uses iterative inorder with early stop. Time is O of h plus k, not O of n. Third, floor and Ceil array O of h iterative track the best candidate while navigating. Fourth, sorted array to BST, always pick the middle element as root. Gate loves asking the resulting tree height, which is floor of log2 of n. That covers advanced BST operations completely. Master these 5 operations and you will be ready for any BST question in exams. For more DSA concept videos with code walkthroughs, download the Selection with Sathi app. Like and subscribe. Thank you.